Okay, Assalamualaikum and a very good night for everyone. Okay, today we want to present about water distribution in oil and gas. For first slide, it's about a design of water distribution network in oil and gas industry. Okay, the first point is about water sources and endpoint. Okay, our water sources is from a water treatment plant, and from water treatment plant, it will be transferred to three endpoint, which is cooling process, process equipment, and steam generation. The distance between water sources and endpoint is 30 meters. And our outlet design is we using separate outlet directly from tank. Okay, this is about our explanation why we using multiple outlet. Okay, we're using multiple outlets because we want making water delivery to efficient become easier. And when using water delivery to a place, it's very become efficiency for water distribution. This is because having multiple dependency can reduce dependency on a single reliable and sustainable water more reliable and sustainable water supply. Like in maintenance issue, the other outlet can continuous, the other functioning continually, providing redundancy. Providing okay, next is about advantages of multiple advantages for the multiple outlet in this design in our design to control the water pressure effectively. Okay, because this is multiple outlet. If multiple outlet are to a single pipe, there may be a pressure as water flow to by having individually outlet, it maintain consistent water pressure for each connection. Second advantages is easier maintenance. For cost, it's high cost because we use a lot of pump, including cost for needs installation. We use a lot of pump. Okay, this is about our explanation why we're using multiple up. The second point, it's about tank location and elevation. Tank location we decide to put at higher level or higher point, which is elevated storage tank. Why we choose to placing tank on high tower? Because we want to get the maximum gravitational forces so that the water flow easily into the pipe. When the tank at higher level, it's allow the natural forces of gravity to produce consistent water pressure throughout of system. In term of the cost, the water tower can reduce the number of pumping station needed, allowing for centralized pressurization and pumping. So from that, it can cut costs for buying many pump. This is our diagram for the water network layout at the oil and gas company. And for more information, it will be presented by Manisha. So I pass this presenter for Manisha.
Next is for pipelines routes. Pipelines used to connect the water sources to the tank and also to connect the tank to the endpoints. In this design, we use sticker line for all pipelines and thick pipeline used for this system. And And then for flow water in high volume, we used huge diameter for pipelines. And then we had chosen the types of pipelines, which is carbon steels, because it's not too expensive than others pipe. However, for these design factors and considerations influence our choice of the specific routes, which is water demand and quality in the system. It's because pipelines to prevent contamination from external sources and minimize the risk of water quality issues. The operation also needed many water to do the processing part. Other than that is maintenance and cost. We choose the routes that using higher cost of the installation, forget the best quality and to avoid from hazardous. Next is required higher velocity. This is because to ensure large amount of water to flow faster through the pipeline to supply for the operation. And next is how the routes impact the efficiency, pressure management and cost effectiveness of the design. First, we've minimized the friction losses and optimized flow distribution can ensure the water reaches all area of the networks and water flow faster through the pipe. Second, we've minimized pressure drops. It can maintain consistent and adequate pressure level throughout the system. Last is higher cost for installation of these routes. This to contribute long-term cost effectiveness and to reduce frequent repair so we can ensure optimal operation conditions. Next part is valve and fitting. In this design, we had marked the location for valve, pump and elbows along the pipelines. Then we had determined the placement and types of fittings along the pipelines. For the valve, we had placed at 4-meter pipeline and also placed at outlet pipeline at 20 meter for cooling system and steam generation and 30 meter for process equipment. For types of fittings, which is elbow, we place at separated part between one pipe to another pipe. The thicker elbow needed for each separated part. A rationale for including fitting which is elbow in our network design is because pipeline after tank are separated into each pipelines, so we use elbow to combine one pipe to another pipe. This ensures the efficiency and reliability to transport the water in this system. And next is factors that influence the quantity and fittings, which is elbows selected is cost considerations. The cost is high because of quantity and the maintenance for these fittings. Then is construction and material standards. The elbow having a good material which is large and thick elbow. Next is hydraulic considerations. This to require the pressure from losses and durable elbow to withstand the force of water. Next is impact the overall design, including effects on pressure management and cost effectiveness because of placement fitting which is elbow. First, increase friction loss. This can lead to higher pressure drops and cause lower overall system efficiency. Second is maintenance cost. When more fittings, it results in higher maintenance costs reach over the time. If the elbow not properly maintained and replaced, this can lead to leaks, corrosion, and other issues such as repair. Next is label and annotation. We had labeled each components with descriptive of text, and we used arrows to indicate the directions of water in the pipelines.
So, I'll start the presentation of the water storage tank first. So from the assignment 1, the height of the water storage tank is recorded to be 80.6 meter. So the velocity is 0. Then we need to find the volume of the water storage tank at the top. So we get the flow rate for the water storage tank at the top, which is 2,300 liter per minute. So we need to multiply it by 24 hours and multiply it by 1 meter cube over 1,000 liter and multiply it to 60 minutes per hour. and then we get 3,312 meter cube. So after finding the volume, we need to equalize the radius that we got, which is the 3,312 equals to pi radius square multiplied by 80.6 meter. So after that, we will get the radius of 3.616 meter, and then we multiply it by 2 to get the diameter, which is 27.233 meters.
To calculate the major head loss, we use the series bridge equation, which is HF equals to F times L over D and times V square over 2G, which is the F is the friction value, L is length, D is the diameter, V is the velocity, and 2G, G is the gravitational acceleration. So for the first outlet, which is cooling system, first of all we have to find the area, which is equals to pi D square over 4, and the diameter is 0.305. So the area equals to 0.073 meter square. Then the flow rate given is 1,500 liter per minute, and we convert it to meter cube per second, and we got 0.025 meter cube per second. Then we must find the velocity using the flow rate equation, which is Q equals to A times V, and we got 0.342 meter per second. And we assume the temperature is at 25 degrees Celsius, so the kinematic viscosity is 0.8927 times 10 power negative 6 meter square per second, and the mu equals to V times rho, and we got 8.927 times 10 power of negative 4 kilogram per meter second. So after that, we have to find the Reynolds number, which is rho times V times T over mu. So 1000 times 0.342 times 0.305 over 8.927 times 10 power of negative 4, and we got 116,847, which is turbulent. And then from the Moody chart, we have to find the friction value, which is we got 0.0215. Then using the Dust-Weber equation, for the first outlet we got the major head loss is 0.0126, and for the second and third outlets, we use the same method, which is for the second outlet we got 4.984 times 10 power of negative 4 meter for the major head loss, and for the third outlet we got 1.4032 times 10 power of negative 3 meter, and for the total major head loss we got 0.0114 meter.
Next, I'll continue the presentation by explaining the calculation for minor loss for each outlet. So for the minor loss, we are going to use the formula of H minor equals to K multiplied by the velocity square over 2G. So the first outlet, we have 4 pump foot valve and 2 gate valve and 4 90-degree elbows. So we need to find the values for K first. So K equals to 4 multiplied by 1.5 plus 2 multiplied by 0.3 plus 4 multiplied by 0.9, and then we will get the value of 10.2, and then the 10.2 is going to be inserted into the H minor formula. Then 10.2 we multiply by 0.342 square over 2 multiplied by 9.81, and then we will get the value 0.060 m. And next, for the second outlet, we have 1 pump foot valve and 1 gate valve, and then we will find the K value first, which is 1.5 plus 0.3, and it equals to 1.8. For the H minor, we are going to insert the K value, which is 1.8 into the formula. So 1.8 is going to multiply by 0.068 to the power of 2 over 2.9.81, and then we will get the minor loss value, which is 0.000424 m. For the third outlet, we have 4 pump foot valve, 2 gate valve, and 4 90-degree elbows. So we are going to find the K value first. It's the same like the first outlet, which is 4. We multiply by 1.5 plus 2, 0.3 plus 4, 0.9, and we will get the values of K, which is 10.2. And the H minor, we are going to insert the 10.2 but into the formula. So 10.2 multiplied by 0.1142 to the power of 2, divide it by 2, multiplied by 9.81, and then we'll get the value 0.0067 m. As for the total minor loss, we are going to sum up all the minor loss for each outlet, which is the total minor loss is going to be 0.060 plus 0.000424 plus 0.0067, and it will equal to 0.0671. So we need to find the pressure for each outlet first. And for the first pressure in the first outlet tank, which is the cooling system, the value for the internal pressure is given 50 psi, and then we convert it to Pascal, and then we will get 344.738 kilopascal. And for the second outlet tank, in the process equipment, 100 psi, we convert it to Pascal, and we will get 689.476 kilopascal. And for the pressure in the third outlet tank, steam generation, the value given is 100 psi, and we convert it to Pascal, and we will get 689.476 kilopascal. And then we sum up all of the value, and then we will get the value for the pressure outlet, which is 1702G.69 kilopascal. And for the pressure inlet is equals to 0. And then if we want to find the change in pressure, just minus the value for the pressure outlet with pressure inlet, and we will get a 1702.3690 pascal. As for the velocity for each outlet, we just sum up all of the total of the velocity for each outlet, and we will get 0.55241 meter per second. As for the velocity, we just minus the velocity outlet minus velocity inlet, and we will get the value 0.5241 meter per second. As for the change in elevation, we just minus the value of Z1 to Z2, and we'll get the value 0.
To calculate the pump pressure head, we use the Bernoulli equation given, which is HP plus P1 over rho G plus V1 square over 2G plus Z1 equals to P2 over rho G plus V2 square over 2G plus Z2 plus delta H major plus delta H minor. And we assume that P1 and V1 are 0, and the elevation for both tanks is the same, so we assume it is negligible. So we got HP equals to P2 over rho G plus V2 squared over 2G plus delta H major and plus delta H minor. And the value of the pump pressure head for the first outlet is 35.22 meter. Since it has 3 pumps, the value of the pump pressure head is times 3. So we got 105.66 meter. By using the same method for the second and third outlet, we got 70.28 meter for the second outlet and 210.87 meter for the third outlet. By increasing the system's pressure, the pumps force the water to higher points, such as the summit of a hill or water storage tower. And then it is also to lift, boost, and regulate water pressure and ensure that it is efficiently transported and distributed to satisfy the demands of different users and locations. So pumps are crucial components of water distribution systems. To conclude, the pumps have two important functions, which is the ability to supply liquid at the required rate of flow and the impart energy to the liquid, thereby increasing the pressure. How do pumps facilitate the movement of water within a distribution system? To facilitate the flow of water via a distribution system, pumps are essential. Distribution systems use a variety of pump types, such as well pumps, which draw water up from below and feed it straight into a distribution system, low lift pumps, which move surface water to a nearby treatment plant, and high lift pumps, which release treated water into a mix. The majority of water distribution pumps are centrifugal, meaning that water is given more energy and pressure inside the pump, causing utilizing an impeller that rotates quickly. Another kind of pump that delivers a set amount of water with each piston or water cycle is the positive displacement pump. The system pressure has no bearing on the positive displacement pump's flow capacity. Pumps supply the necessary pressure for the water in distribution mains and multi-story buildings to reach the necessary height. So by generating pressure differential between the apparatus input and exit, a pump transfers fluid. This pressure differential is produced by the pump's piston, impeller, or other moving parts, which also force the fluid through the pump. The efficiency of different types of pumps can be understood in terms of their performance curve, pump cavitation, and net positive suction head, which is NPSH. The performance curve shows the pump's efficiency at different flow rates. To save energy costs and prevent undue impeller wear and tear, it is critical to make sure the pump is operating at or close to its best efficiency point, which is PEP. Cavitation, or the creation of vapor cavities in the liquid because of low impeller pressure, can be brought on by running the pump at low flow rates. cavitation can shorten the life and dependability of a pump by causing vibration, noise, and decreased performance. So to avoid cavitation, the NPSH is an important factor to consider when choosing a pump and should be higher than the pump's NPSH requirement. Net positive suction head required, or NPSHR, is the lowest pressure needed on the pump section side to prevent cavitation. So to avoid cavitation, which can shorten the pump's lifespan and performance, make sure that the NPSHA, which is net positive suction head available, is higher than the NPSHR. To conclude, pump properties such as the capacity to generate high heads at low flow rates or high flow rates at low heads are shown by the forms of the pump curves.
Next, I'll continue the presentation by explaining the pump process. So pumps actually facilitate the movement of water from one place to another. So their main purpose is to transfer water over long distances or to overcome obstacles in pipelines to reach higher or lower areas. Besides, pumps are also used to increase the water pressure in distribution system. So this is important to ensure that each tank in industry get water at the right pressure, especially in areas with differences in height. Pumps are also used to push water through pipelines and to overcome friction losses so that it can reach each tank in the industry at the end of the distribution system. So next, the consideration that should be considered when selecting the appropriate type of pump for a distribution system. So the first consideration that should be considered is the flow rate requirements. So to ensure a consistent and sufficient supply of water or fluid, it is important to determine the necessary flow rate of the distribution system and ensure the pump's capacity and that matches the expected demand. The next, pressure requirements. So we need to determine the necessary pressure levels at different locations in the distribution system at the oil and gas industry. So we need to choose pump that can generate the required pressure in order to meet the system needs. So as for the working principle of the chosen pumps, and the pumps that we chose is centrifugal pumps. Centrifugal pumps are widely used in the oil and gas industry for various applications such as cooling system, process equipment, and also steam generations. So the working principle of centrifugal pumps involve the conversion of mechanical energy into kinetic energy and then into potential energy within the water. So first, the pumps will create a centrifugal force by spinning the impeller within the pump casing. So when the impeller spins, it will generate a centrifugal force inside the pump's casing, which is it will push the water away from the center of the impeller toward the outer edges. And next, the fluid gains more energy as it moves from the outer edges of the impeller due to its spinning motions. Then, the fluid will gain kinetic energy as it moves radially, and the impeller will give the fluid velocity. After leaving the impeller, the fast-moving fluid will enter the volute casing, which is a chamber that gradually expands in a spiral shape around the impeller. So the fluid slows down and its pressure increases in this chamber. The fluid slows down as it passes through the volute casing and converting its kinetic energy into pressure or potential energy. And the widening of the volute casing will cause the fluid to slow down, which result in an increase in pressure. The pump increases the pressure of the fluid and pushes it out through the outlet. And this pressure is strong enough to overcome any resistance in the system, such as friction in pipes or changes in elevation. So the impeller's continuous rotation will guarantee a consistent stream of fluid through the pump, resulting in a dependable and constant supply.
Okay, we proceed to safety measure for industrial application. Okay, for safety measure, it involves two application, which is pressure relief valve and surge protection. Okay, for pressure relief valve, typically it's configured to operate at maximum permitted pressure. If the valve detect a higher pressure, within the system, it will open up and release the excess pressure. In case the system medium is toxic, the escaping pressure may be captured. However, when it is safe, the pressure can be allowed to escape into to the atmosphere. For such protection, in order to protect electronic equipment from voltage spike or transition, it's important to take preventative measure. This can help avoid any potential damage to the equipment. The surge protector contain metal varistor to absorb excess voltage and shunt the excess current to ground.
Then, environmental impact assessment for industrial oil and gas. We anticipate the environmental benefit of this design to manifest, which is reduced water consumption. By implementing more water distribution system to reduce the overall amount of water used in industrial for processing to conserve water resources. Second, reduce energy consumptions. By minimizing friction loss and optimize pumping requirement to reduce the overall energy consumption. This to reduce greenhouse gas emissions. Next is specific ways in which the design will contribute to more sustainable resource usage and reduce the environmental impact within these industries. First, having a leak detection and repair. This can incorporate advanced leak detection technologies such as ultrasonic sensor and smart meters, and also can reduce water loss and minimize the environmental impact from waterways. And last, renewable energy sources. This can help minimize the carbon footprint and reduce the greenhouse gases. This to conserve of natural resources and help combat climate change.
So the next, I will explain the example of energy efficient pumping practices that will align with the demands of oil and gas industry's operation. The first, efficient pump selection. So choosing pumps that are appropriately sized for the specific application and operating conditions. High efficiency pumps, such as those meeting the standards of program, like a pump energy index (PEI), should be considered. So the impact, the properly sized and efficient pumps consume less energy and can lead to long-term energy savings. The next, system optimization and regular maintenance. So regularly inspecting and maintaining pumps, pipelines, and the control system to identify and fix inefficiencies promptly. So optimizing the entire pumping system can lead to energy savings. So by doing that, we can improve system efficiency that ensures the pump operate at their best performance and reduce the energy waste and the likelihood of unexpected breakdown.
To engage stakeholders and foster a culture of environmental awareness, we plan to educate and train the employees about the importance of sustainability, responsible water usage, and the potential impact of industrial activities on the environment. Then we also establish clear sustainability goals and targets and communicate them to all stakeholders, as it can help create a shared vision and a sense of purpose. Lastly, we implement sustainable best practices such as efficient water use, waste reduction, and recyclable and sustainable materials. Initial investment costs, resistance to change, and the requirement for continual monitoring and reporting to guarantee compliance with sustainability standards and regulations are some of the problems that might arise when implementing sustainable practices in industrial contexts. Sustainably adopting sustainable practices can also be difficult due to the complexity of global supply chains and the requirement to interact with many stakeholders in various geographical areas.